Okay. All right then. So today we are not meeting in lab because we are not actually doing any lab projects. We're actually just going to be talking about the topic in general. Today's topic is infrared spectroscopy, and this is something that unfortunately we don't really get to do this semester, but if you take 223B or if you take the actual organic chemistry lab later on, the 320, I believe, you actually get to do a lot of infrared spectroscopy problems. But next semester, you will definitely do it. We do have the IR machine. Some of you who have been into the little hallway where we've done the the UV light for the TLC, you will see that the machine is right behind you. And it's actually a very small machine, very straightforward, easy to use. But unfortunately, they don't think that it's necessary to do this semester. So if you do want to do it, either join a research group or watch some videos or take 2 to 3B. You will definitely get a chance to do it next semester. But the reason we're spending some time to talk about infrared spectroscopy is because this is one of the ways that we analyze our compounds and we confirm what we have. So one of the questions that you guys had on the quiz was, what is exactly does it measure? It measures two things. Number one, it measures the vibrations of the bonds, and it also measures, well, it doesn't measure, but it tells you what functional groups you guys have. So by looking at the specific signature of the IR spectra, you could specifically tell me whether you have, for example, a carboxylic acid, or if you have a carbonyl, or if you have an aldehyde, or anything of the sort. So this is very important, and you will see why we can use this technique to identify molecules. And at first, you might not make much sense of it because all you see is squiggly lines, but once we show you what to look for, you'll be much better prepared to identify what exactly it is you're looking at. So let's get into some quick background. So spectroscopy, it's a Latin word composed of two parts, spectro meaning image and scopy meaning to look, like a telescope. So this is simply is we're looking at an image of a molecule, and more specifically, we're measuring what happens to this molecule when we shine electromagnetic radiation on it. There's different areas of electromagnetic radiation. Us human beings, we have eyeballs, and we can only see a very, very small fraction of infrared radiation of electromagnetic radiation. We can only see visible light, which is usually 400 to 700 nanometers. You can see all of the colors of the rainbow are there. Some animals are capable of seeing ultraviolet light. I know birds and bees are usually good at seeing UV light. I know that snakes and other sorts of reptiles are very good at detecting infrared radiation, which is how they can find you in the dark. We use some radiation to cook our food. For example, microwaves are a type of electromagnetic radiation, also photons, but they're called microwaves because the wavelength is a lot larger. And of course, I know you guys don't listen to the radio anymore, but we also use radio waves to transmit information. If you go to the doctors, you do X-rays, and then if you go into space, you get bombarded with what's called gamma rays and X-rays and cosmic rays and all sorts of things that will give you cancer. So it's a large spectrum, and we only see a very, very small amount of it. That is the visible light. So we have to create instruments that we can use to detect all sorts of other information that all of these other um, wavelengths can give us. And so you see down here, there's a relationship between wavelength and frequency and also energy. You see that the speed of light, c, is equal to the wavelength times the frequency. It's a proportional relationship. We also have all these other equations. H is the Planck's constant, which is just a constant value. You can look it up. C is the speed of light, which is also considered constant. And then the wavelength just depends whether you're measuring it in meters, in nanometers. Generally, we measure visible light in nanometers, but as long as you know your metric prefixes, it doesn't really matter what you use. And you can also see that, frequency and wavelength are inversely related. High frequency, remember a wave it goes up and down. So high frequency means that you're just going up and down a lot faster. Low frequency means that you're just going up and down in amplitude a lot slower. So longer wavelengths, because they are a lot longer, they take longer to go up and down. So long wavelength is usually associated with low frequency and vice versa. A short wavelength means you go up and down a lot quickly, and that's why you have the relationship. And of course, high frequency waves are considered to be higher energy than low frequency waves. So this is just something that you should keep in mind. And of course, you can always look at the chart and use this for your reference. So then we get into absorption of electromagnetic radiation. So what is happening here is we are taking a photon of energy and we are taking this photon and shining it at a molecule. This molecule either will reflect it, absorb it, or diffract it, whatever it is, depending on the size and depending on the wavelength. In this case, we use infrared radiation because it just so happens that the energy of the infrared light matches the energy of the vibration of a chemical bond. and that is why we use infrared. We also use UV vis to do other types of analysis depending on the molecules. Some molecules are more UV active than others. You could see in the TLC experiment that when we shine UV light at a molecule, it absorbs, and that's why you see a dark spot. So UV vis does something very similar to that. In this case, IR uses the infrared radiation, and you can see that it takes uh, a lower energy state to a higher energy state. And the delta E is just the difference in energy between those states. Some molecules will not vibrate until you reach a very specific level of energy. And once you have that level of energy, it'll absorb all the energy. So if you're measuring the absorption of that energy, you can use an instrument to detect what percentage of that energy was absorbed. And that's what gives you your spectra. So this is just a quick review of Chem 111A. You know, we have what's called the low energy or ground state, and if we have enough energy of just the right amount, we can excite it. That is the proper term. We excite it into a higher energy state, and then the higher energy state eventually relaxes to the lower energy state. And so it says here exactly what I just said. For absorption to occur, the energy of the photon has to match exactly the difference of the energy between the two states. If it does not match that energy, you do not get an absorption. So that's why even though you can start, for example, at 780 nanometers all the way to 1 millimeter, not all of that energy will get absorbed by the molecule, only specific wavelengths. And that's exactly what makes IR so powerful, is that it allows us to tell what functional groups are present because some functional groups only absorb at very specific wavelengths, which we will see as we continue. And then, yeah, I already said all this. Okay. So anyway, and as I mentioned, we have an entire range of electromagnetic spectra. You can see here, some of you guys asked me last week, actually, what's that machine in the room? The one that has like a giant tube and it says, you know, don't get near it because it has a giant magnet. That is called a nuclear magnetic resonance spectrometer, or NMR. Again, if you take 223B next semester, you are going to be playing with the NMR a lot. But that one uses radio waves. IR uses infrared. So to answer the pre-lab quiz question, IR means infrared radiation. So that is what we are going to be looking at. It measures the functional groups and the bond vibrations of those functional groups. NMR specifically tells you about carbon and hydrogen atoms. And then if we want to do UV vis, it tells us if there's any conjugated systems. A conjugated system is just an alternating single and double bond in a molecule. So that is very optically active and UV active as well. So again, we'll learn about this another time. Right now, we want to specifically focus on IR spectroscopy. And also, by the way, if you guys have any question at any point during the presentation, simply click on the raise hand and I will get to that, or you can type the question in the chat. Okay, so here we go. Infrared spectroscopy. This is how we find out about functional groups. So the energy gets absorbed by the bonds. The bonds, we can think of it, if you guys have taken physics either in high school or so far in here at Long Beach, you have learned about something called the harmonic oscillator. And that's just a fancy way of saying a spring. If you guys have ever played with springs from the pens or the springs from your shocks in your car or just a general spring, you'll notice that it has this motion, a vibrational motion. And when you plot this motion, it actually creates a wave-like motion, which is why we can use the electromagnetic radiation to activate that vibrational motion. So in this case, we can think of the chemical bond as a spring. And this, at the end of the spring, you have two different atoms of different masses. So it could be something like a light atom like H and a heavy atom like Cl. But more specifically, we have a carbon-carbon bond, and that carbon can be bonded to either another carbon. It could be double bonded. It could be triple bonded. It could be bonded to an oxygen. It could be bonded to a hydrogen. All sorts of these bonds emit IR signatures. So for this case, in order to understand IR spectroscopy, you have to consider the bonds of a molecule like springs that go back and forth. And just like real life springs, if you've ever played with a spring, not only does it just oscillate in and out, it can also wiggle around all sorts of ways. And that's exactly what molecules do. Often we show you guys pictures of molecules, and the molecules are just static. It's just a picture. But in real life, these are moving. They're constantly moving, they're constantly vibrating, they're constantly wiggling around. And I'm going to show you guys some animations so you can see this. But it is these vibrations that we want to take a look at. And it is these vibrations that when we shine IR radiation at the molecules, we can actually see their signatures. So that's basically what it is. We plotted over the range of wavelengths, and then once we do that plot, we can measure the absorbance or the emission or the transmittance, and then that's when we can see the IR spectrum. And then this is what the instrument actually looks like. It's a very small instrument. I've seen some that were a lot larger, but those are usually the older models. As you know, technology advances to the point where we honestly have something like this the size of a laptop or even smaller. It's relatively straightforward to use. That little dot in the center, you usually put a drop of your molecule dissolved in a solvent. The solvent is usually acetone or DCM or chloroform, depending on what it is. And then you simply put the little device down and then you shoot it with IR radiation, and that's when you get your spectra. And if you look below, you see this is what the spectra looks like. You'll see that we have percent transmittance on the y-axis, and we have the wave number on the x-axis. And you can see the peaks are upside down because as the peaks get closer to the ground, that tells us how much or what percent of the light was absorbed. So percent transmittance tells you how much of the light went through, but also how much of the light got absorbed. So you can see here, if you look at the number close to 3500, that's close to about, I would say, 10% transmittance. That means 90% of it got absorbed. And that's why we get that peak. So these are what we consider absorption peaks. And these absorption peaks are what we look at. And depending on the intensity of the absorption and the size of the peak, that is what tells us what sort of functional group that we have. So this is a generic higher spectra. And there's a lot of mathematics that goes into it. I think the most important one is the fact that we're measuring things in inverse wavelength. Inverse wavelength. We do not measure it in general wavelength. We take the wavelength of our IR photon and we take the inverse of it, and that is what we call wave number. And the wave number, even though I told you guys earlier, usually we measure things in nanometers. In this case, for some reason that is historical, I'm sure, they decided to measure it in centimeters. So when you see wave number on the x-axis, just know that the formula for that is 1 over the wavelength in centimeters. So one of the questions you might get on your final exam or in the future as you continue is, what is the wavelength of absorption of this chemical bond? Well, you simply take the inverse of the wave number and convert it to meters, and that gives you the answer. And as it says here as well, wave number is directly proportional to the energy. So the higher the wave number, the higher the energy. You could think of it as if the spring that you have is a very stiff spring, you need a lot more energy to vibrate that spring compared to a spring that is weaker. You can just simply blow on it and it'll start vibrating pretty quickly. And so we measure usually from 4,000 centimeters to the -1 to 400 centimeters to the -1. So you can see also the scale is not necessarily linear. I think the scale is a little bit exponential. You see that the 400s and the 1,000s are a little bit um, not as close together compared to the 4,000s and the 3,000s. So this is just the way that they have it. We just have to learn how to read it, and we have to be able to look at the patterns. So are we okay so far? Everybody good? No questions, nothing? Just give me a quick thumbs up. Okay, sounds good. Like I said, at any point, if you have questions, simply raise your hand, type in the chat, or unmute, and I can go ahead and answer that question. Okay, so again, why do we use IR? Well, first of all, it's harmless. If you get an infrared photon on your skin, it's just going to feel a little bit warm. In fact, IR radiation we feel and perceive as heat. So this is why we use it. We don't want to shoot radio waves at you guys, even though that's also harmless. We don't want to shoot X-rays or UV light at you guys because that definitely will damage your cells and your DNA. But IR is relatively harmless. It's cheap. It's easy to produce. And more importantly, though, the molecules, the bonds of the molecules. Notice I keep repeating this point because this is the whole point of IR. The bonds of the molecules vibrate at the same frequency as a photon of infrared light. And that is what tells us what type of bond it is, depending on what atoms are present in the bond, and therefore the functional groups present in the molecule. So, since all bonds are different in a molecule, for example, a ketone might be a carbon oxygen, but that carbon might be attached to a nitrogen or to another carbon. They produce very unique IR spectra, almost like a fingerprint. So each organic molecule has its own unique infrared spectra, and that is why we use IR. And then, of course, like I keep mentioning, we can determine what sort of functional groups are present in the molecule. One of the things that we do have to keep in mind is that there has to be a dipole moment in the molecule. So if you have something, for example, like carbon dioxide has a carbon in the center and two oxygens on the side. It is a linear molecule. Since it is symmetric and there is no net dipole, it is not IR active. There has to be a dipole moment present in the molecule in order for the vibration to be detectable by the IR instrument. So the more polar the bond, the more intense the absorption will be. So this is something you have to keep in mind. So all of the diatomics, H2, N2, Cl2, Br2, you cannot see those on an IR. So just keep that in mind. Some molecules, even though they are polar bonds, they are overall nonpolar. Those molecules, you will see either very little absorption or none at all. And we consider those infrared inactive. There is another form of spectroscopy called Raman spectroscopy. That one actually measures the rotation of molecules. Those you could see with Raman spectroscopy. But for regular, just everyday IR spectroscopy, you cannot see molecules that do not have polarity. So make sure you keep that in mind. The greater the change in the dipole moment, the more intense the absorption, the stronger the peak will be in the spectra. And you can see here, CH is smaller than NH, which is smaller than OH. And so as the polarity increases, the intensity also increases. Does that make sense? Everything okay so far? You just need polarity. If the bond is not polar, you will not see it. There has to be a dipole moment present in the bond. And so this is where it starts getting more interesting. Again, we measure that we mention that you can think of a bond as a spring, and the spring is vibrating, but not just vibrating in and out. It also wiggles around. It also just wags around. And these are actual terms that we use. We call it wiggling. We call it wagging. We call it stretching. We call it bending. All sorts of twisting, all sorts of words that describe the motion of a spring with masses at the end of it. And so I actually have a few animations that I want to show you guys if I can stop sharing the screen here real quick. So let me see. I'm going to see if I can do this. I want to go to the other tab right here. Okay, so this is a website called CHEM223A. I use this website a lot because it has a lot of really cool animations. This is an example of one sort of vibration. This is called ethylene. This is C2H4. You see, usually we look at this molecule, two carbon atoms, four hydrogen atoms. But again, in the real world, molecules are always moving. They're not just static. They don't just stay like a picture and you're like, yeah, I'm just here. I'm a molecule, not moving around. They're constantly wiggling. They're constantly vibrating. They're constantly um, bouncing in and out, up and down. And this is one example of that vibration. It kind of looks a little funny, but that is the point. The point is that there's all sorts of different vibrations that molecules have. So this is one of those. If I go and click next, you can see here's another type of vibration. This is what would be considered an asymmetrical twisting vibration. And you can see there how the bonds move asymmetrically and they're being twisted about the double bond. Here's another type of vibration. This is an in-plane twisting. You can see here that the atoms of hydrogen are being dragged down also asymmetrically. Some are being dragged up, some are being dragged down. Here's another example. This is what would be called scissoring, where you have the molecules kind of just coming together like a pair of scissors and then also just spreading apart. And this would be called a symmetric scissoring because you can see the top and the bottom are both bending in and out at the same time. So all sorts of different things. This would be an asymmetric scissoring. You can see that they're both going in the same direction, but they're not exactly symmetrical to each other. And then here's another example right there. So, and of course, the more complex the molecule, the more bonds you have in the molecule, the more types of vibrations you will have in the bonds, and therefore the more peaks that you will have in your IR spectra. So, for example, here's carbon dioxide. Let me see if I can do that. You can see carbon dioxide has these sorts of stretches, but because it's considered nonpolar, only a few of these stretches are actually visible. It's the ones that are asymmetric because when you have an asymmetric stretch, you actually change the polarity of the molecule a tiny little bit. So you get a very, very slight absorption, but not too much. So here's an example of the carbon dioxide bending. You can see this one, the carbon molecule kind of like bends down and the oxygens kind of stay in the plane. Here you see another one also in the y-axis plane. Here you see another one where the two bonds of the carbon dioxide are like coming out away. This is more like the spring-like motion. Here's another example. This one is more asymmetrical, so this one kind of like waves and wiggles like in and out. And all of these absorb the energy and show up as peaks. But only the asymmetric ones for this specific molecule will actually show up because that is disturbing the dipole moment. So again, this is just another example. Let's take a look at water. Let me see. Click on water. I'm clicking water, but it's showing carbon dioxide. Okay, let's try ammonia. Well, that's not exactly the one I was looking for, but here's another example. For example, boron trifluoride. If I click next, you can see here you have like a sort of like wiggling of the molecule, and then here you have another wiggling, and then here you have another one right there. I'm not sure. There we go. Methane. Here's another one. Methane is a pretty good example. So there you have one sort of motion of the methane molecule. Here you have another motion, and then here you have another motion right there. And all of these are happening simultaneously. Molecules are very small. They absorb a lot of energy very readily. As long as you're not at absolute zero, the molecules are moving. So this is something that we need you guys to start thinking about from now on. When you look at a molecule, you don't think of it as a static molecule anymore. You need to think of it as moving. The pictures that we show you, it's like we go with a camera and we take a picture of the molecule and we show you what it looks like for the sake of analysis, for the sake of presentation. But in real life, this is the real motion of molecules. So just keep that in mind as you continue through your career. And then I think the last one I'll show you here is benzene. Even though benzene is a flat molecule, it still has vibrations. And you can see here you have the vibrations of the hydrogen atoms. So the whole molecule is kind of wiggling. Not too much because the double bond is considered a little bit stronger, but there's definitely a lot of wiggles around there. And you can see all sorts of vibrations, symmetric and asymmetric, in plane and out of plane. This would be an out of plane vibration. Does this make sense? Like, are you guys okay with this concept so far? Just thumbs up or smiley faces or anything? Okay, sounds good, sounds good. And then, so yeah, so this website is CHEM223A. You can go on this website whenever you want and take a look yourself. There's another website I want to show you guys, which is this one here. This one, the animations are not very good. They're kind of like low resolution, and then they're using like an old like applet. But again, here, this one summarizes all of the vibrations of all sorts of molecules. And you can go here on the left and click, for example, on formaldehyde. You could see all sorts of different vibrations. It tells you exactly where they are in the wave number spectra. You could click, for example, this other one. And of course, you can see that the most basic molecules only have one sort of vibration. And remember, diatomics do not show up in IR at all. So HCl, that one will show up. HBr, that one will show up. HI, that one shows up. F2, it's symmetrical. There is no net dipole. This one is not IR active. And sure enough, you can see right here, IR inactive. When they are inactive, we use the other type of spectroscopy that measures the rotation of the molecules. That one is called Raman. So this is something that when you guys are making molecules and analyzing them, if you don't see something in the IR, you can say, well, we're going to have to try another type of spectroscopy. So hopefully this makes some sense. This is a website from Purdue University, and you guys can just go on Google and type it in any single time and find out. But hopefully this helps a little bit in understanding those vibrations. I find I'm a very visual person, so whenever I see something like this, it really helps me a lot. So I'm gonna go back to the PowerPoint now. Give me a quick second. And then I believe I was right here. Okay. So yeah, so this is a lot, those images and animations were a lot better than simply just looking at this slide right here. But this is what this slide was trying to illustrate, the fact that the molecules are constantly in motion. And some vibrations have higher frequency than others, and those vibrations will absorb at a higher wave number compared to other ones. So hopefully this makes some sense. Again, if you have any questions at any point, simply raise your hand, ask me, come to office hours. I will be more than glad to explain. And so this is just kind of explaining the physics behind it. You guys don't really need to know this. It's mostly for those people who are like physics majors or who really care about like the intricate details. But again, this is just showing you how we can take a general molecule, model it as a spring model with two masses at the ends. And if we do some chemical formulas, we can derive some interesting information. The important thing from this slide right here is that the strength of the bond tells you a lot about what type of bond it is. So we learn in Gen Chem 1, single bonds are longer and weaker than double bonds, and double bonds are longer and weaker than triple bonds. So triple bonds are the strongest and the shortest bonds, so they are going to vibrate at higher frequencies, therefore higher wave numbers. And so depending on where you see those vibrations, that tells you whether the molecule has a triple bond, a double bond, or a single bond. And it also tells you the masses of the atoms. So for example, if you have like a carbon bonded to a chlorine, well, chlorine is heavier than carbon. Chlorine has a molar mass of about 35, whereas carbon has a molar mass of 12. So it's almost 3 times as heavy. So you're definitely going to see some difference versus just a carbon-carbon bond. So you can prove that by simply substituting the masses into the equation here, the reduced mass equation. But again, it's very intuitive once you learn what to look for. So you don't necessarily need to know this. But in terms of details and covering our bases, this is one of the reasons that we have this slide right here. So we can go ahead and move on to the next one. So here we go. Now we have an actual example of a real IR spectra. And this is what it looks like. And so right now it looks like a bunch of squiggly lines. At the end of the presentation, you're going to be able to look at this and be like, oh yeah, I definitely see an alcohol. I definitely see an sp3 CH bond in here. So you can see here that the three things that we look for in the IR spectra are the wave number. In other words, where exactly is the peak located? The shape, is it sharp? Is it pointy? Is it broad? Is it rounded? That tells us a lot of information. And also the intensity. Is it a very low absorption? Is it a very high absorption? Those things give us what we need to know to determine the functional groups and determine what our molecule is. And as a disclaimer, you cannot tell me the structure of an organic molecule based solely on the IR spectra. That is just not possible. You either need to know, you have a suspicion of what it is, like you have something and you know it's an alcohol, so you're going to look for an alcohol signature. But you can't look at a spectra. Nobody can look at a spectra and tell you, oh yeah, that's definitely this molecule just based off the spectra. Like that's not possible. You always need supplemental information. So if somebody tells you that they know, either they've been working with IR long enough that they have that information in their head, or they're just flat out lying to you. But you cannot tell the structure of a molecule solely on the IR spectra. You always need more information. Okay, so here we go. Now we can actually start learning how to interpret this. So you can see here, depending on what sorts of bonds you have, you absorb in different regions. So single bonds have this region below 1400. We call that the fingerprint region. Um, it's not really that useful. It's kind of good if you have nothing else to go off of, but the fingerprint region is kind of just there. It's kind of like I mean, think about it. Organic molecules inherently by definition are mostly carbon, right? So you're going to have a whole bunch of carbon-carbon vibrations throughout the whole molecule. That doesn't really tell us much. We know it's an organic molecule. We'll most likely know what the molecule is, like how many carbons are present. And so the fingerprint region is kind of just there to look at. If we really have nothing else to go off of, it's a good place to take a look, but it is not the first place we look. The fingerprint region is kind of just more like, well, that's some noise. It still gives us important info, but we usually don't really take too much of a look at it. It's still a good idea to know where it is. Usually it's anywhere below 1400 down to 600. More importantly, double bonds, for example, carbon-carbon double bonds, alkenes, ketones, carbon-oxygen double bond, amides, so carbon-nitrogen double bonds, are present between 1600 and 1800. That is very important, especially the carbon-oxygen double bond. You guys are going to be recognizing that immediately because it's very characteristic. It is found pretty much in the same regions, and it is one of the go-to fingerprints. So you'll usually see a band in between these regions that will be a carbon-oxygen, carbon-nitrogen double bond, and it has a very large absorption. So it is a very strong peak, and depending on what sort of molecule is there, you can often see that it is going to be either a little bit broad, a little bit round, but sometimes it's very sharp. So again, you don't just look at this blindly. You kind of have an idea what your molecule is, and this is more of like a way to confirm it. For triple bonds, you usually don't have a lot of absorption. Remember, triple bonds are shorter and they're also a lot stronger. So it takes a lot more energy to make them vibrate. They will absorb energy, but they'll usually not have a lot of absorption. So usually this will be at around 60% transmittance to 80% transmittance, and it is a very sharp peak. So you will see that with the carbon-carbon triple bond, carbon-nitrogen triple bond. And more importantly, and this is the region that really tells you a lot of info, is anything to the left of 2500. So from 2500 to 4000 you will see the nitrogen hydrogen bending, wiggling, twisting, the oxygen hydrogen bending, wiggling, twisting, the carbon hydrogen sp3, sp2 um, vibrations. And anything to the left of 2500, you usually produce very broad, very large peaks. And these are the ones that give you a lot of good information as well. So I will give you some examples, but this is good to know. This is very good to know. I would definitely take time to internalize this because if you're going to continue with organic chemistry, you're going to see this a lot. So make sure you keep this in mind. You could always go on Google and they'll give you many examples of where this is, but this is a good thing to keep in mind. And then another thing we have to consider too, when we're looking at molecules without any functional groups, is that we're still going to see some signals. Carbon hydrogen is still considered a somewhat polar bond, so it is going to absorb a lot of infrared radiation. And so you are going to get some sharp peaks. And remember, single bonds, sp3 hybridized, double bonds, sp2 hybridized, triple bonds, sp hybridized, and also the shape and the size. Triple bonds are shorter, double bonds are a little bit longer, single bonds are the longest of them all. So depending on the type of bond, depending on the hybridization of the molecule, you will have your peaks in slightly different regions. And you can see here that as you go from increasing P from P to S, you have a shift in the absorbance. So you see that alkynes are going to be at a higher wave number. Remember, triple bonds are smaller and stronger. So they are going to vibrate at a high frequency. Double bonds are a little bit less. So you see here the triple bond is at around 3,300. You see the double bond here shifts to about 3,100. And then you see here the single bond actually gets blended in somewhere between 2,800 and 3,000. And so if you have no other functional groups, you could still get some information about the types of bonds in the molecules based on the absorbance of your infrared radiation. Does that make sense? Thumbs up or smiles or something? Okay, one thumbs up, two thumbs up, three thumbs up. Okay, sounds good. Sounds good. Just make sure you guys are still there. Alrighty. So yeah, so just because you have no functional groups doesn't mean that you can't get any info. And actually, this is what a standard alkene, alkyne, alkane IR spectra looks like. You're often gonna see this peak right here from 3,000 to about 2,700. It kind of looks like a hand, like a stalactite from a cave. And usually you will see the rest of the spectrum is kind of just not really that interesting. Like there's nothing after 3,000. There's nothing between 2,700 and 1,500. So if you have a spectra and it kind of looks relatively boring, you can make a good guess that there's probably not a lot of functional groups. That doesn't mean there's nothing happening. It just means you don't have a carboxylic acid. You don't have a primary or secondary amine or things like that. But you do have to pay attention to where the peaks are. So I can tell you right now, just based on looking at this specific spectra, since I don't have any peaks to the left of 3,000, this is just a single bond alkane, nothing else going on. So this is probably propane, this is probably methane, this is probably butane, not really much going on there. So hopefully this also makes some sense. If not, again, feel free to ask any questions. So again, here's an example, octane, not a lot of stuff going on. You have a CH3 band at 1400, which is the fingerprint region. Again, since we got nothing else going on, then we do take a look at the fingerprint region. But we usually know what we're kind of expecting. The most important thing when looking at alkanes is the region here, again, the stalactites that you see, the CH2 stretching, the CH3 stretching. You see it's very intense because CH is a polar bond, so there is a lot of absorption. So you will see that between 2,800 and 3,200, and again, nothing else. So if you see a spectra and it looks like this, you most likely just have an alkane, alkene, or alkyne. When it comes to aromatic compounds, we do consider benzene a functional group, and it's for a reason. You can see here that if we have just toluene, which is nothing but carbon and hydrogens, the spectra looks a little bit different. And also we have the carbon-carbon double bonds, but also we have resonance effects. So the resonance makes this double bond more like a 1.5 bond. So it weakens the bond. Resonance weakens bonds. And so the entire wave number gets shifted to a lower number. So you see here we have this peak somewhere in between 3,000. That is called the ARH stretch, the aromatic hydrogen stretch. That is just the between this carbon here at the vertex of the benzene and the hydrogen there. The CH3 stretch is always going to be there. Like the CH3 stretch is always there. I mean, if you point it out, even though it's nice to know, no one's really going to be impressed. They're going to be like, hey, look, there's a CH3 stretch. Cool, bro. What else is there? The most important part for aromatic rings is this one right here, the aromatic carbon double bond stretch. That is going to be between 1400 and 1600. It is very strong and it is a lot lower than a standard carbon-carbon double bond absorption because remember, because of aromaticity and because of resonance, that double bond is not really a double bond. It's more like a 1.5 bond. So make sure you keep that in mind. And again, since we got nothing else to go off of, these people actually want to point out stuff between 650 and 800. CH bending. Well, that's cool. CH bending. Of course, there's going to be CH bending. There's nothing but CHs in this molecule. So not particularly impressive, but still good information to know. So again, just keep that in mind when you're looking at a molecule. You're not going to go in blind. You already know you're working with something that has a ring, so you're going to be expecting these kinds of peaks. So we have other types of functional groups. There we go. We have aldehydes, ketones, esters, carboxylic acids, amides. All of these have a characteristic carbon-oxygen double bond. And like I mentioned, this is actually, I think, one of the most important information you can get from an infrared spectra. The carbon-oxygen double bond vibrates strongly because it's very polar. Oxygen is one of the more electronegative elements of the periodic table. And so that gives us a very, very strong absorption. And because of the way that chemistry just happens to come together in the universe, all of these lie between 1700 to 1800 in the wave number. So depending on your specific functional group, you will often have, for example, the amides at the lower end, carboxylic acids around 1710, ketones at 1715, aldehydes 725, esters at 735, 1735, anhydrous stuff 1760, 1800s, and then 1810s. So depending on which specific type of carbonyl functional group you have, you're going to have that carbonyl peak at specific regions, but always in a very narrow range of the spectra. So this is the first thing that most people who learn IR start recognizing right away. Like you look between 1600 and 1800 and you're like, that's a carbonyl right there. The skill comes in when you tell me what type of carbonyl. Sure, it's a carbonyl, but is it an ester carbonyl? Is it an aldehyde carbonyl? Is it a carboxylic acid carbonyl? There are other fingerprints in the spectra that will give you that information. But the carbonyl itself is always very distinct. You almost can't miss it unless you don't know it, in which case it's very apparent that you don't know it. So make sure that you also know this, you also keep this in mind. And of course, these vary, right? These vary. This is not absolute. Sometimes you have a ketone that is not exactly at 1715. It might be a little bit further up, a little bit further down. That depends on what the rest of the molecule is. But in general, it is in this region and it is very, very apparent. And here's a few examples. You can see here we have two types of carbonyl compounds. We have 2-heptanone and we have butyraldehyde. So you see the carbon oxygen stretch is there at 1718 and look at the intensity. That is at 5% transmittance. That means that almost the entire energy of the photon was absorbed by that carbon oxygen double bond. And if you look at the bottom one, similarly, you see that has maybe 4% transmittance. Almost all of the energy of the photon was absorbed by that carbon oxygen double bond. And you see they're both relatively strong signals. They're very sharp. The bottom one is a little bit less sharp, but it is that sort of information that tells us if it's simply just a regular ketone versus an aldehyde. And of course, if you look at around the 3000 region, you will once again see the stalagmites. That's just carbon hydrogen stretching. That is present in every organic molecule because every organic molecule contains carbons and hydrogens. So make sure you know that it's there. Make sure you know that what it is and what it isn't. That there's other signatures that look very similar to the CH stretches, but make sure you know what it is. And then when it comes to aldehydes, there is a very peculiar signal for that CH stretch on that terminal hydrogen. That is usually found a little bit to the right of 3000. So you can see here it's present at 2820 and 2720. So that would be your carbon hydrogen aldehyde stretch. And then, of course, the most important part of this is that carbonyl stretch, the carbon double bonded oxygen at 1700, 1718, 1720. Very distinct, very iconic. You guys can't miss it. Like if you see that there, your first thought should be that's definitely a carbonyl compound. But what type? That's when you look at, for example, the CH stretch for the aldehyde or for other stuff. And then, as I mentioned, when you have conjugation effects, when you have resonance, that turns any double bond into a 1 point something bond. So it weakens the bond. So if you can see an example down here, we have a regular ketone, just carbon oxygen double bond, no double bonds nearby. That's at 1720. But when you introduce resonance or conjugation, the definition of conjugation is alternating single and double bonds. So whenever you guys hear that word conjugated, just think alternating single double bonds. Another word or another concept related to conjugation is resonance. If you have conjugation, you most likely have resonance. So anytime you introduce resonance or delocalization, you weaken the bonds and therefore you lower the wave number. And this is what I was trying to tell you. The carbonyl might be a ketone carbonyl, but depending on what's around it, that might change the wave number. So make sure you keep that in mind. You don't just keep it in your head that it's one number only and nothing else. You have to take a look at the entire molecule. Does this make sense? Are we okay? Thumbs up? Thumbs down? Yes? No? All right. I see at least a few. Okay. Good to know you guys are still here. Alrighty. This one is where it gets more distinct. Alcohols and phenols. A phenol is just an hydroxyl group with a benzene ring. So if you have benzene with OH, that's called phenol. If it is just a regular OH in a regular chain, no rings, that is called hydroxyl or alcohol. It is very distinct and it is always going to be above 3000. So if you look right here at this example, one hexanol, you see this very broad, smooth peak. That is your OH stretch. And the reason that it is broad is because if you remember from GenChem, anytime you have NH, FH, or OH, you create hydrogen bonds. And those hydrogen bonds lock the molecules in place even more. And so you need a lot more energy to make those vibrate. And that is why all of the OHs are present at very high wave numbers because you require a lot of energy to vibrate those specific bonds. But also because of the not only do you have the oxygen hydrogen bond itself, you also have the hydrogen bond that is vibrating. And so that creates a very large range of absorption for these types of signals. And that is why you see instead of having a very sharp, strong peak, the peak gets broadened and it gets smoothed out. And so whenever you have an IR spectra and you see this specific broad, smooth peak around 3200 to 3600, you can bet that is an OH. That is an OH functional group right there for sure. Like this is distinct. There's nothing else that makes this specific signature right here. And then, of course, if you look over here, you also have a carbon oxygen stretch. We don't really look at that because that could be anything. That could be a carbon-carbon double bond vibration. That could be a carbon oxygen ester vibration. In this case, since we suspect it's already an alcohol, we can point to it and say, ah, yeah, for sure, there's the carbon oxygen bend right there. But without that OH information, we can't really point to that and be like, yeah, this is definitely it right here. And then you also see a peak between 1400 and 1600. Some people might be tempted to say that's a carbonyl, but remember, carbonyls absorb almost all of the energy. The fact that this is at 40% absorption means that is not a carbonyl. So make sure that you don't confuse your molecules either. This is probably some carbon double bond something, but hexanol doesn't have a double bond. So actually, we don't know what that is, and we don't claim to know. That's something else. We don't just make things up. If we don't know, we don't know. Sometimes we take an IR spectra just to confirm a single functional group. Remember, you can't look at a spectra and tell me the identity of the entire molecule. You need way more information for that. The IR is just one part of the whole. So just keep that in mind. And then a little bit on the family of alcohols is the carboxylic acid. The carboxylic acid is COOH, so it does contain an alcohol. So you still see the broadening of the signal. You see over here, starting at around 2500, the signal gets very broad and it doesn't stop until about 3500 in the wave number. So if you see a signal that is extremely broad like this, and also you see at 3000, you also have the CH3 stretching, the stalagmites I was talking about. When you combine these two, it almost looks like a beard. And so this is actually what organic chemists call this specific fingerprint. They call it a beard. So if you see the beard in the IR spectra, you bet that you have a carboxylic acid. It's very distinct. You can't miss it. And then, of course, carboxylic acids also have that carbonyl, carbon oxygen. Again, notice the intensity. The CO, the C double bond O, absorbs almost all of the energy of that photon. So you get a very strong peak at around 1700. So whenever you have a carboxylic acid, you will see the very strong carbonyl peak, and you will see the beard starting at 2500 all the way to 3500. And what else can we get out of this? Honestly, not much, because this broad signal will also obscure a lot of other signals. But we know for sure from this spectra that we have a carboxylic acid. And the fingerprint region, you see, it's kind of all over the place. And this is one of the reasons we don't really pay a lot of attention to it, because I mean, if we know we have a carboxylic acid, this is most likely going to be an oxygen hydrogen stretch or bend or twist, carbon oxygen bend or stretch or twist. All we care about is this carbonyl and this OH that looks like the beard. Those two tell me carboxylic acid. And the more you do, the more you get trained at this, the better your eyes become. So every time you see this and you see the beard, right away you're like carboxylic acid. I know that's carboxylic acid. And so let's see, dibutyl ether. This is ethers, and ether is a carbon oxygen carbon functional group. Here, the only thing you can observe is just carbon oxygen stretching. So notice that even though the intensity is strong, it stops at around 20% of transmittance, and it is not at 1700. It is a lot lower. It is between 1000 and 1200. And so that is what makes it distinct from a carbon oxygen double bond. Remember, double bonds are shorter and stronger, so you need more energy to make them vibrate. So they are going to appear at a higher wave number, not at a lower wave number. And then, of course, if you look over here at 28, between 28 and 32, you will see the standard stalagmite of the carbon hydrogen sp2 sp3 stretch. So doesn't really tell us much. If you know you have an ether, you're gonna look for most likely this carbon oxygen stretch. Definitely not at 1700 because it's a single bonded carbon oxygen. So make sure you keep that in mind. The intensity matters, the wave number matters, and the location matters. What are these two right here? That's probably another type of carbon oxygen twist. Like the stretch, remember, is actually like the sandwich motion. This is probably like a twisting motion or like a bending motion, and it doesn't absorb a lot, so we don't really pay attention to this. This is just at 2800, it's just CH3, CH2. So we just kind of ignore that. We kind of just look at the important ones. And then here we have ethyl butyrate and methyl benzoate. So again, once you start getting more functional groups in your molecule, your spectra starts looking a little bit more complicated. Again, if you go between 2800 and 3200, you will see that carbon hydrogen sp2 sp3 bending. In the first example, ethyl butyrate, we do have a carbonyl group. You can see the structure right over here on the left, on the right, I'm sorry. And you see that CO carbonyl stretch. Again, note the strong intensity. Only 10% of it got through. 90% of it was absorbed. So you know this is a carbonyl. It is between 1600 and 1800. So in the 1700s, definitely a carbonyl. And if you have that, you also have a CO stretch somewhere else. That could be any one of these peaks, but usually it's the stronger one of the peaks. I don't know about the peak close to 1000. I would personally debate that one, but the one at 1200, definitely a CO. And then for esters like methyl benzoate, you have multiple things happen. So for example, again, if you look between 2800 and 3200, I think you're starting to get the gist of it. These are just regular CH stretches. Again, look at 1700, you have your carbonyl peak right over here. Since we know that there are carbon-carbon double bonds, if we look between 1400 and 1600, we see those peaks that correspond to the double bonds in the benzene ring. And then for esters, not only are we looking for the carbonyl peak, we're also looking for two carbon oxygen peaks, usually between 1000 and 1300. And sure enough, you can see down here that at around 1300, you have that very strong carbon oxygen peak, almost the same intensity as a carbonyl, and you have a smaller but very sharp carbon oxygen stretch. Esters are carbon, oxygen, oxygen, carbon. So you could think of an oxygen as a bridge between two carbons. Those are very polar bonds, so they have a lot of absorption. That's why you see these peaks. And then there's one more peak here at around 700. You see it's very sharp, very strong. Again, that could be the oxygen carbon methyl stretch, that could be the carbon oxygen wiggle, that could be the bend. It's really hard to say. So again, we don't really pay much attention to the fingerprint region. If we need additional justification, we can point to something and kind of say, yeah, I think that's most likely this one. We kind of care more about the stuff above 1000. And so you can see here, based on this, you can get a lot of information about what functional groups you have. Are we okay so far? Any questions? Anything? Any points of confusion that I can address? Thumbs up if you're okay. I see one thumbs up. I see a clapping. Thank you. Alrighty. Okay, good, good. You guys are here. Thank you, thank you. Appreciate it. Okay. This one is really cool, in my opinion, because this one is directly related to the actual structure of the compound. Amines, this is just NH or NH2. Make sure you don't confuse those with amides. Amides are carbonyl and amine. Amines are just NH2 or NH. And we have two types. We have primary, which means there's only one carbon nitrogen bond. That is primary. Secondary means there are two carbon nitrogen bonds. So primary is only one carbon nitrogen bond. Secondary is two carbon nitrogen bonds. And then depending on whether you have a primary one or a secondary one, that will tell you how many peaks you get in your spectra. So if you look at this at the spectra of hexylamine over here on the left, this is a primary amine, meaning you have two NH stretches, and you can actually see two peaks that correspond to the two stretches of the amine. And so by doing IR, you can tell me definitively whether you have a primary amine or a secondary amine. And they are both roughly in the same location. They are always going to be above 3000 in wave number. So if you look at the one, for example, piperidine, that is a nitrogen with two carbon bonds. So there's only one NH stretch. You see that single peak right there at about 3400. And if you look at hexylamine, you have two NH bonds. So you're going to see two peaks. And those are the peaks that you see right here at around 3400 to 3500. So amines are one of those compounds, just like alcohols and carboxylic acids, that are very distinct in an IR spectra. And then, of course, since a tertiary amine, in other words, a nitrogen with three carbon bonds, since that one does not contain any NH stretching, that one will not show up. So if you see a peak above 3000 that has two peaks or a single peak, and you know you have an amine, you can tell me what sort of amine it is. If you don't see anything in there, but you know there's a nitrogen, you're going to have to look for a carbon nitrogen stretch, and that is going to be at a lot lower wave number than this one right here. So this is, I think, one of the more distinct and useful tools to determine what sort of amines you have in your compound. So make sure you keep this in mind. I notice a lot of people get these confused. They get these backwards. They think, oh, I have two peaks, so it is a secondary amine. No, two peaks means you have two NH bonds and one N carbon bond. So make sure you don't confuse the two. This is where a lot of people lost points on the final. So make sure you keep this in mind. This is very important to know. And so now this is pretty much all of the info you need. At the beginning of the presentation, I showed you the spectra, and it looked like a bunch of squiggly lines. Hopefully by now, you can kind of start knowing what to look for and telling me some information. So this is where you guys tell me in the chat, or if you want to unmute your microphone, what functional groups are present in this specific spectra. So you guys go ahead now. What is present here? What do you see? Type it in the chat or unmute the mic, but you guys got to tell me what you see here. Okay, so I'm getting some answers at 3000 carboxylic acid, correct. I got another answer. It says ester and carbonyl. There's definitely a carbonyl for sure. Is it an ester? I'm not exactly sure. Hold on, I think I messed up the slide here. Oh wait, no, there it is. Yeah. So definitely I'm getting a lot of the same answers. You can see carboxylic acid. Yes, I have some questions like carboxylic acid question mark. Yes. Somebody said carboxylic acid at 1700. Not exactly. Not exactly. At 1700, you have the carbon oxygen double bond. That's a carbonyl. A carboxylic acid contains a carbonyl, but it is not solely a carbonyl. So make sure that you look at the whole spectra and then put the pieces together. You do have the beard that is characteristic. Oh, and I'm not sharing the screen anymore. Give me a second. There we go. I'm not sure what happened there. Okay, can you guys see the screen or let me stop sharing real quick? I think I messed that up. Here we go. Share. Okay, here we go. We're back on track. Okay, yeah. So over here at 1700, that strong, intense peak, that is your carbonyl peak. And then you have the characteristic beard of the carboxylic acid. So what is this molecule? I don't know exactly, but I know for sure there's a carboxylic acid in here. Hopefully that makes some sense. You guys good? I have a question. It says, would the peaks between 1200 and 1500 matter? Only if we don't know anything else. Those could be carbon hydrogen, those could be carbon oxygen bands. Most likely, those are carbon oxygen stretches, but since we know we have a carboxylic acid, we just know that they're there and they're present. So, yeah, and also if you guys could please direct your questions to everybody so everybody can see the questions you're asking me because everybody is sending me questions directly and other people can't see the questions you're asking. So, please make sure that when you ask a question, you ask the question to everybody on the chat. But yeah, so based on what I have been getting, you guys are correct. This is definitely a carboxylic acid in this molecule. Okay, so moving on to the next slide. What about this one? What do you guys see here? And remember, please post your chat answer to everybody so everybody can see your response. What is here? You guys got to tell me. Okay, yep. Aiden says OH at 3500. Okay, great. Anyone else? How do we find the peaks again? You look at it. You're looking at the spectra, and whatever is sharp and down at the bottom is considered a peak. So, if your question is, how do you know what peak it is? There's always tables that you can reference that will tell you what functional group vibrates at what wave number and therefore what peaks. Zane said amine. This is not an amine because you can see the absorption is very strong compared to the amine. So this is definitely not an amine because it's a very, very broad signal. Amines are usually a lot narrower and they are not as strong. They are usually very weak peaks. Alkane, well, by definition, everything that has a carbon hydrogen chain is considered somewhat of an alkane, but we're looking at specific signatures of functional groups. So in this case, Aiden was definitely correct. You have this broad, kind of medium strong signal at around 3500. That is characteristic of an OH functional group. And since you don't see the bottom peaks right there, there is no beard. That means this is not a carboxylic acid. The peak at 3000, that is just your standard run of the mill carbon hydrogen sp3 stretching. And since there's nothing else between 1500 and 3000, this is strictly a molecule with only an alcohol functional group. So it's probably butanol, or it's probably pentanol, or hexanol, or something like that. Okay, what about this one? What do you guys see here? Remember, we kind of don't pay much attention to the 1000s region. We kind of start paying attention between 1500 and above. So what do you guys notice here? What do we see here? Can't move on until you guys say something. CH stretching, yes, yes, and that is good. It's always going to be a CH stretch. It's always going to be that stalagmite pattern at around 3000. That is always going to be a CH stretch. And then Daniela asked, is it an amine? It is definitely an amine. You see, you get the very distinct amine peaks between 3300 and 3500. What type of amine? Is it primary? Is it secondary? It tells you right there. You can look at the number of peaks. Primary. Yep. Three what? I don't know what that means. Three. Does anybody else agree or disagree? It's okay. We're still learning, so that's the point. Yeah, so I only see two peaks right here. If you look at between 3400 and 3500, you see two very weak peaks that are kind of a little bit sharp. And those two peaks correspond to your nitrogen hydrogen stretch. And since there's two of them, that means that nitrogen has two hydrogens and one carbon bond. Since it has one carbon bond, it is a primary amine. And then what is that pattern at around 3000? What is there? What do you call that? Zanaya said it earlier. These peaks right here at 3000, what are those? CH stretch, exactly. Yeah. There's always going to be the CH stretch here. So it's very important to be able to recognize that it's there. But if you're not specifically looking for it, then, you don't really pay too much attention for it. And then Zane has a question. He says, are we looking for aromatic as well? Like if it was above 3000, would it be considered an aromatic CH stretch? Well, the aromatic stretches are usually between 2500 and 3000. So if it's above 3000, it is not going to be an aromatic stretch at all. In terms of the CH stretches of the aromatics, again, unless you already know your molecule has a ring, there's no real way to tell if it's a CH stretch of an sp2 or an sp3. We kind of just know and justify it based on what we suspect it already is. Remember, you can't look at a single spectra and tell me the entire identity of the whole molecule. It's just part of the whole information that you need. But if I'm looking at this spectra right here, the main and really the only thing I see is those two peaks, which correspond to a primary amine nitrogen hydrogen stretch. So if you saw this and you looked at those peaks and you thought amine, your brain is already in the right direction. Okay, moving on to the next one. What do we see here? That's right, secondary amine. And why an amine? Because you have that singular kind of weak peak, but it's still very sharp. It's kind of like a sharp peak. It's at around 50%. That's not considered very strong. There's only one of those peaks. It is above 3300, so that is characteristic of a secondary amine. That is a nitrogen hydrogen stretch. I will note there is kind of like a bit of a broadening here, so it is very possible this is an amide. In other words, carbon, oxygen, nitrogen, hydrogen. But if you look at 1700, you will notice there is no carbon, oxygen, carbonyl peak. So therefore, it is not an amide. As far as I know, this is just a nitrogen, hydrogen connected to a carbon. We don't know what this is. We would have to see the picture of the whole molecule. And then once again, I've asked you guys before, I'll ask you again, what are these peaks here at 3000 and 2700? What is that? CH, exactly. Those are just carbon hydrogen stretches. It could be sp2, it could be sp3. If you have a good idea of your molecule, you can justify it. But just right off the bat, we can't really say. Remember, carbon hydrogen is considered a polar bond, so it does have very high absorption. But the most important information from this one is we have that amine secondary amine peak right here at 3300. Okay, next one. This would be unknown number one. If I was to give you, for example, something like this on a post-lab quiz, possibly next week, what would you guys tell me that this is? What are the functional groups that are present in this one? Okay, so Zane said carboxylic acid. Well, if there were sharper peaks at the bottom of that broad peak, remember, it's supposed to look like a wizard's beard, right? I know some beards are kind of rounded, but you kind of have to think of like a scruffy, not well taken care of beard. This is not a beard. This is just a general broad peak. So it is not a carboxylic acid, but you are on the right path. There is an OH in there. And yes, everybody keeps answering. That is definitely an alcohol peak right there. What are the peaks at 3000? What are the peaks at around 2800 to 3000? What are those? CH stretches, exactly. See? So you see now how we're starting to see these things and we're like, well, that's a CH stretch. That's always where the CH stretches are at. But the most important part is that broad. Notice how it's broad. It goes from around 3,100 all the way to around 3,800. That's a very broad range. It's strong because oxygen hydrogen is a very polar bond. And so that is the characteristic OH peak. If you see something that looks like that with no spikes at the bottom, in other words, no scruffy beard, that is almost always going to be an alcohol right there. So, and then you notice there's nothing between 1,500 and 2,800. So this spectra doesn't really tell us much else. Sometimes we do a spectra for a single functional group, and this would be one example of that. Okay. How about this one? Unknown number two. What do you see here? Okay, CH stretches, of course. There's always CH stretches, right? At around 3,000. Primary amine? Question mark? I don't know. What do you guys think? Secondary amine? I don't know. What do you guys think? No. Okay, good. Why not? Why is it not an amine peak? C double bond to H. Aiden, good. Yes, this there's a peak at around 1,700 that is very sharp but not very intense. I would say that's most likely a carbon-carbon double bond. But without knowing the structure of the molecule we're working with, we cannot 100% confirm. But when I saw this, I looked at that peak and I was like, well, it fits the region of the carbon-carbon double bond. The carbon-carbon double bond is not that flexible, so it's not going to be absorb a lot of energy, so it's not going to be very intense. So this is definitely an alkene or an alkane of some sort. There's not really much else happening here. And then, of course, if you look at the peak at around 3,100, that is probably a carbon hydrogen double bond peak right there. Remember, you have your alkane, you have your alkenes, you have your alkyne. So depending on that shift that you see, that'll help you make a distinction. So now that I see the peak at 1,700, that is very weak but very sharp, and the peak at 3,200, that is very weak but also very sharp, I am a lot more convinced that this is actually an alkene of some sort. There is a double bond, at least one double bond present in this molecule right here. Does that make sense? Like, you guys understand what this is? And the reason that it is not an amine is because the peak is sharp. Amines produce peaks that are like kind of rounded at the bottom. If it's a super sharp peak, it is not an amine. Amines are a little bit more rounded at the bottom. Okay. What about this one? What do we see here? What functional group do you think you have here? Carbonyl, right? And where is that carbonyl at? Under 2K. I need you to be more specific. There's a lot of peaks under 2K. Okay. Yeah, it's about 1,700-ish, right? I would say maybe 1,720, 1,730. So we know it's a carbonyl. This is where the real skills come in. What type of carbonyl? Is it just a regular old ketone? Is it an aldehyde? Is it an ester? Is it an amide carbonyl? Like, what are we looking at here? Ester. Why do you say it's an ester, Aiden? Around 1715. Good, good. Can you point to maybe more evidence besides that? Because remember, it's not absolute. They could be shifted a little bit higher or lower depending on what else is attached to that. Did we look at the shape? Yes, you look at the shape of the peak. If it's very strong and sharp, then that tells you one thing. If it's not as sharp but still very strong, that tells you something else. So yeah, you always look at the shapes of the peaks as well. And then Aiden said something to do with the absorption band at around 3,000. Well, at around 3,000 or so, remember, what's at 3,000? Whenever you see the stalagmites, what is usually at 3,000? Exactly. CH stretches. Exactly. So
Be in class right now.
every
I'll
time
be
you see
looking at
those,
fucking OChem.
every time you see those peaks at around 3,000 or so, um, you will always think of those as CH stretches. So most of the time we ignore that because it doesn't really give us too much information. But there is a very distinct signature here that tells me what kind of carbonyl it is. CH, does that mean this is a carboxylic acid? No, this is not a carboxylic acid because you do not have a broad peak that looks like the beard. If this was a carboxylic acid, the broad peak would start at around 3,000 and it would go all the way to around 3,800. It would be strong, so it would be very broad, very strong. And at the bottom, you would have very sharp peaks. Remember, it looks like a wizard's beard. If it does not look like a wizard's beard, it is not a carboxylic acid. But good guess. So, anybody else, what type of carbonyl do we have? Zane says CO stretch at 1200. Good. This very sharp peak right here, this is definitely a carbon oxygen stretch. So this could be an ester, or this could also just be some other carbon oxygen interaction stretch. But this makes a very good case for an ester. There is one more peak that is very distinct. I'll give you a clue. It's not a very strong peak. It is somewhere above 2500. Then I said, why is that an ester? Because esters contain two bonds with a carbon. You have the carbon oxygen double bond, that's a carbonyl, and then the carbon oxygen single bond of the second oxygen. That carbon oxygen single bond will usually be located between 1200 and 1400 as a medium intensity peak. So that one right there does look like a carbon oxygen bond. So it makes a good case for definitely having an ester. And then I had a request for showing what a carboxylic acid looks like. So I will go ahead and do that. Let me go back real quick. This is what a carboxylic acid looks like. See, it's very broad. It's very broad. It overshadows almost everything else after 2500. And you see those sharp things at the bottom. This is what I'm talking about. It's like a very scruffy beard. This is what we call the beard. If you don't see this very broad region of very high absorption with the little peaks at the bottom, it is not a carboxylic acid. Carboxylic acids are very distinct. It has to look like this or it's not a carboxylic acid. So now you see the difference between this one here and unknown number three that we were doing right over here. So you see how you don't have that broad peak? That's why it's not a carboxylic acid. And just as a reminder, please direct the questions to everyone in the chat so everybody can see the questions you're asking. Okay, the last thing I want to show you is this peak right here. This peak at around 2800, that could be a carbon hydrogen peak. So again, we can't really tell for sure unless we know the structure of the molecule, but you can make a case that this is an ester or that this is an aldehyde because this peak right here, this little peak, that is very characteristic also of an aldehyde group. So it's possible that this molecule might have both. You could have a carbonyl of an ester and a carbonyl of an aldehyde. You could have an aldehyde and a carbonyl. We don't really know. One of the downsides of IR is it doesn't tell you how many functional groups we have, just that they are there. So we would need more information to definitely know what these peaks are, but we do know there's a carbonyl peak for sure, and we know there's either a CO peak at around 1200 or there's an aldehyde CH stretch at around 2800. So make sure that you remember you can't always tell everything just from a single spectra. Okay? What about this one here? What are we seeing here? So the question was, if we label for labeling these on the lab, will we get points off if we only classify the peaks that are obvious? So the thing is, we are looking for the obvious peaks because that tells us what the functional groups are. Um, CH3 are obvious, right? Point them out. Tell me that those are CH3s because some people will confuse the CH3 peaks with the carboxylic acid peaks. Tell me that you know the difference. So definitely label them. And then the next question was, can you tell us the steps you do when identifying? The steps is you look at the graph, you see the shape, you see the intensity, and you see where they're located. At the end of the presentation, and also just in general, you have a table, and that table tells you where the specific peaks are in the spectra. Honestly, the only real way to get good at this is just to keep doing it. And I'm going to show you guys something like that at the very end as well. So this is really just a matter of practice. The more you do it, the better you get at it. But yeah, make sure you label the peaks. And sometimes you have to take a shot in the dark too. Again, this is kind of difficult because I'm not giving you guys the shape of the molecule. But when you look at this, when you do this in lab, you kind of know what you're expecting. So when you look at this, it'll either confirm that you made the right compound or it'll tell you that you got it wrong and you have to go back and try again. So you're not just gonna go in blind. We don't just give you nothing but a spectra and have you tell us what the molecule is. That would be very unfair. So what do we see in this one? Unknown number four. Alkane. Yeah, there's not much happening here. This you can see it's a relatively boring spectra. We have the characteristic sp3 stalagmites, and then we have like a very sharp peak at around 1500 that most likely corresponds to a CH stretch. Not very exciting spectra. This is probably just a regular boring old alkane. It's probably butane, it's probably hexane, it's probably octane, decane. Not much else happening here. If you were expecting a functional group when you're doing a synthesis and you see this spectra, something went very wrong. You'll have to go back and figure out what happened. So yeah, this one's very straightforward. It's just a regular boring old alkane. What about this one here? What do we see here? Yep, yep, exactly. Primary amine. There you go. See, you guys are getting better now. You don't see squiggles anymore. Now you're starting to know where to look, right? So Zanaya, you asked me earlier, what are the steps to identifying? Simply look at the spectra and tell me what stands out to you. So in this case, you guys looked at the spectra. You saw there were some peaks at around 3,300. You saw there's two of them. You saw they're not very strong. They're broad. They're a little bit broad as well. So you thought amine. What type of amine? How many peaks are there? There's two peaks, so that means there's only one carbon nitrogen bond, so it is a primary amine, and that is definitely correct. And then if you look at 3000, once again, sp3 stretches, not very useful, but still there. And now that we know there's an amine, if you see the peak at around 1500, that peak is probably going to be a carbon nitrogen stretch. But we can't tell for sure. Honestly, that's not very important. What is important is these two peaks right over here that tell us it is a primary amine. So very good job. Very good job. You guys are getting much better at this. Okay, and I think we have one more. What about this one? What do we see here? Hmm. Definitely. Anybody agree or disagree? Yep, exactly, exactly. It is a very broad signal. Very broad signal. Whoever took this IR didn't do a good job because you see most of it is already like at 60% no matter what. So whoever took the spectra would have to do it again. Ideally, we want to have like most of it baseline at around 90, but we can still get some information out of it, right? So you know how sometimes in lab we do TLC and we don't exactly get the points to be small and we get some smudging. We could still sometimes get some information even if we don't do things 100% correctly. So this is one of those examples. Whoever did this IR did not do a very good job, but we can still get some information out of it. We see there is a very broad signal starting at around 2700 all the way to 3700. That is characteristic of a carboxylic acid. We have a beard-like structure that peaks at around 3000 or so. And we also have the carbonyl peak at around 1700. So the carbonyl peak, the broadness from 25 to 35, and the beard-like characteristic tells me this is definitely a carboxylic acid. Does that make sense? All right. Awesome, awesome. And I think that was the last unknown. Yes. So again, the question earlier was how do we identify the peaks? How do we know where to start? We look at a chart. So unless you want to like dedicate your life to IR or you're an organic chemist and you're doing IRs regularly, we always consult a chart. I don't know if they're going to give you a chart uh, on the final. I'll ask, but some of these are so characteristic and iconic that I mean you'll just know when you see them, unless you're not practicing. Remember, so the more practice you do, the more spectra you look at, the better you will get at doing this. And it definitely helps when you know the structure of the spectra. So you can find all sorts of tables like this on the internet. You can just go on Google and type in table of IR spectra. I think your textbook has some of these. If you bought the organic chemistry as a second language book, I think there's also a table. And some tables have more info than others. And remember, these are general guidelines. These are not 100% absolute. Like if you see something at, for example, like you see SP2 3150, it might not be exactly at 3150. It might be at 3000. It might be at 3200. It might be at 3250. You have to take these as general guidelines. Allow for some variation in these peaks, but this is one of the ways that you do it. And this is the end of the slide. So I am going to stop sharing the slideshow here. And I want to show you one more thing before we end today. Let me go back to here and share. Okay, so this is again, remember we have ChemTube 3D. This is where you can see the actual vibrations of various different molecules. We have the Purdue website where you can select different molecules and look at their vibrations as well. It would help for sure to know what they look like. But most importantly, I want to show you this website right here. And hold on, I think I'm having some issues with the sharing. One more time. Here we go. Share. Okay, so this website right here, if you guys are going to take Chem223B or you are going to take any advanced organic chemistry in the future, this is a very good website to keep in your bookmarks. It's called the Spectral Database for Organic Compounds. It is a Japanese website that has basically a database of all sorts of IR, NMR, Raman, mass spectrometry spectra for almost every single molecule you can imagine. So for example, I'm going to come over here and in the compound name, I'm simply going to type acetone. So check this out. Acetone and then search. And then you have to agree to the disclaimer. So make sure you agree. You're going to get a list of all these results. The very first one you see over here where it says compound name, that's acetone right there. Right here where it says IR, it says Y. That means there is a spectra available. I'm going to click that and you're going to see an IR spectra of acetone. And so you can see right there the IR spectra of acetone. And sure enough, at 1700, you see the carbonyl peak that corresponds to that acetone right there. And that is the most distinctive and important peak of acetone. If you have acetone, you're looking for that carbonyl. If you don't see that carbonyl, there's no way it can be acetone. So again, sometimes we take a spectra for a single or a single functional group and nothing else. So yeah, and then if I want to try this again, I would just go back and let me see. Let me search something else up. Let's look up. Oh, we were doing acetylsalicylic acid, right? So acetyl salicylic acid. I think I misspelled that. Here we go. Acetylsalicylic acid. So let's search that up and see what it looks like. Here it is. IR spectra, yes. And you see the structure right there, and here's the spectra. So again, you have that very distinctive stalagmite CH3 sp3 carbon hydrogen stretches. And then you have your carbonyls. So note that in acetylsalicylic acid, you have two types of carbonyls. You have your ester carbonyl and you have your carboxylic acid carbonyl. So you'll see here at 1700, you actually have two carbonyl peaks. One is lower than the other. And so this is where you kind of have to look at the polarity of the molecules and be like, okay, well, this is probably this peak, this is probably that peak. I will tell you the broader peak is most likely the carboxylic acid carbonyl peak. The sharper peak is most likely the ester carbonyl peak. And you see here that there is a broad signal. It's not very strong relatively, but there's still kind of like a beardish pattern. It's not very strong because the signal from the ester group also kind of is present, but you still see kind of like a beardish pattern. But I'm gonna be honest with you, if I didn't know the structure of salicylic acid, this beard would not be enough to tell me that there's a carboxylic acid there. So this is one of those examples where you kind of have to already have in mind what you're expecting so that when you see it, you know if it's there or not. So in a way, IR is almost like a confirmation method. It's not really like a deductive method. Like we don't look at it and be like, oh, I believe I made this compound. I believe I made that compound. No, you already kind of know where you're heading. You like if you're trying to convert something to a carboxylic acid and you see this pattern, you're like, well, that looks beardish enough that I'm convinced there is a carboxylic acid there. But if you're just looking at it blindly, it's kind of hard to tell, and this is very distinctive. Let's do one more. Somebody give me a molecule, and I'll type it in. something in the chat. Any molecule you guys are interested in? Anything that you want to ask about? Maybe something with an amine. Actually, I just thought of one. Let's do hydroxylamine. Hydroxylamine, because that has an OH and an NH. So hydroxylamine. And then you click search, and here it is, hydroxylamine. And oh, sorry guys, they do not have an IR spectra. So, but they do have a spectra for hydroxylamine hydrochloride. So let's take a look at that one. Okay, so there we go. So you once again you see that there is that OH broad peak. It kind of looks like a beard, but hydroxylamine does not have a carboxylic acid. So, but it is an amide because it's just a hydroxyl with an amine. So like it does create like a carboxylic acid kind of effect, but not exactly. This is starting to get a little more out of the scope of the introductory, but I'm just trying to show you like what it looks like. So there should be an amine peak. It's very weak because it gets blended into the hydroxyl stuff, so you can't really see it very well. So, I mean, I guess this wasn't really the best example to show you guys, but spectral database for organic compounds. You can type in all sorts of compounds, click on the IR spectra, or you can click over here on the box. You can see it says IR only. And just take a look at all sorts of compounds. And then the more you see it, the more you play around with it, the more you rationalize it, the better you get at doing this. And hopefully by the time the final comes around, you guys will at least be like at least pretty decent at this. And then next semester in 223B, you will definitely be doing IR a lot more. So this is something definitely worth remembering. And I just got a request. Can I put the link in the chat? Yes, I can. The link is right here for this spectral database. So make sure you save that in your bookmarks. And then when you start learning how to do other types of spectroscopy like NMR or IR or mass spectrometry, you will also be able to use this a lot. I still use this to this day, which is why I'm telling you guys about it. And I will probably look up at some spectra from here to give you guys for your quiz next week. So make sure that you are practicing, taking a look at examples. And then if you have any questions, of course, come to office hours or ask me, send me an email, and I'll be more than glad to help you out. So this concludes today's class. Thank you guys for showing up. I really appreciate it. Thank you for taking the quiz. And again, I will see you guys next week. So make sure next week we are starting Lab 5. So make sure you do the procedures as always. Make sure you're studying for the pre-lab quiz. And just be ready to start the project. And we'll, of course, we'll talk about it beforehand. There is going to be an IR post-lab quiz. So make sure you study IR. And it's also going to show up on the final. So just because we don't do anything right now doesn't mean we don't have to remember it. We do have to learn this because it does not go away. So that is everything for today. So if you guys have any questions or anything, stick around. Otherwise, you guys are free to go. And thank you for coming today. I really appreciate it. And I will see you guys next week.